In simple harmonic motion, we consider the case where the total energy of the system remains constant. In this section, we'll now look at two more realistic examples of harmonic motion, starting with the first case, damped harmonic motion. In real life, all harmonic systems will experience some amount of damping. This is energy loss, and it can be due to friction or air resistance forces. Generally, a simple linear drag model like this that I've written on the board, F drag equals negative BV, where V is the velocity, can model the drag force. This would be a system that once set into motion, it loses energy so that it eventually comes to a stop. In that case, it's in damped harmonic motion. And the differential equation for damped harmonic motion has three solutions that we'll look at now. The first case is underdamped motion. This is where there are small amounts of damping so that once the system is set into motion, it will oscillate with decreasing amplitude so that it eventually comes to a stop. The graph for damped motion of displacement versus time for underdamped motion would look something like this. So the amplitude of the function is decaying with an exponential decay envelope. So that's why I've drawn these exponential decay lines here. And it decreases within those lines, eventually decreasing to zero. And many real life systems fit into underdamped motion. If you were to use a pendulum in a lab, for example, if you displaced that pendulum and released it, in the air there would be damping. It would oscillate, but eventually if we left it, it would come to a stop. And that's underdamped motion. Okay, I've drawn the next two on the same graph so that we can compare. If we were to then increase the damping, eventually it will reach a point of critical damping. If the system is critically damped, then it has the least amount of damping possible that will cause the system to not oscillate. So when displaced, it will simply return to equilibrium in the shortest amount of time possible. So an example of this is shock absorbers, because the goal of shock absorbers would be to stop the oscillation as soon as possible. So that would be critical damping. If the damping is increased, then anything over critical damping is overdamped motion. In overdamped motion, the system still does not oscillate. It returns directly to equilibrium, but it takes longer. So this is the blue curve here. It's taking longer to return to equilibrium. An example of this is if you remember our pendulum from the lab that was underdamped. It was underdamped in air. If we were to then take that and maybe put the pendulum in water and then release it, it would return to equilibrium, but fairly slowly. So that would be overdamped motion. So there isn't any math that you need to do for this section, but you do need to be familiar with the different types and the shape of their displacement versus time graph. In order to keep a system oscillating that would otherwise be damped and returned to rest, an external driving force can be added to add energy to the system and to keep it in periodic motion. This is called forced harmonic motion. And if a system is oscillating on its own, then it oscillates at its natural frequency F0. We've seen already the natural frequency for the pendulum and the spring, and just to recall, for the simple mass on a spring, it's here 1 over 2 pi root k over m. So when an external driving force is added, now the system will oscillate at that external driving frequency. So something interesting that happens is that when that frequency is equal to or very close to the natural frequency of the system is in resonance. When a system oscillates in resonance, it will have the largest possible amplitude. So we know this naturally. A simple example of forced harmonic motion is pushing a child on a swing. So if that child was just left on their own, eventually they would come to a stop in damped motion. However, if we push that child on the swing, we can add energy to the system and keep them oscillating. So when we do this, we would naturally kind of stand at the back and push them every time they reach their maximum amplitude. So what we're doing is matching the natural frequency of the system because we know that that produces the largest amplitude. And that's what happens in resonance. So when the driving frequency is close to or equal to the natural frequency of the system is in resonance. Another example of this is why some buildings are affected more by earthquakes than others. If the vibrations of the earthquake happen to be close to the natural frequency of the building, then it can experience larger oscillations. Of course, there's more factors that go into that as well. Another common physics example is the Tacoma Narrows Bridge. I'll include a video after this. So that was a bridge in Washington where it's a famous bridge collapse. And what happened was the wind speeds matched the natural frequency of this suspension bridge and caused large oscillations. There are also some other factors that were due to the construction of the bridge that led to that, but I'll include the video here.